This is Dr. David Brown from Pellissippi State Community College, and this podcast is on binary and is part of a podcast series that I'm doing as part of a class at Pellissippi State, Introduction to Information Technology. The slides that you see to the right are part of a comic book textbook that I have created and used for that class. So anyway, this podcast is on binary. The first part of this comic textbook chapter begins with talking about information and how information can be encoded as numbers. I'm going to skip past that part and really move on to just discussing binary. So it's assumed that if you're taking this class, you've already gone through this part that talks about how all different types of information can be encoded as numbers. Graphics, audio, video, software, letters, numbers, everything can be encoded as numbers. Now, the next question then becomes, how do those numbers get stored on the switches that we talked about in the previous podcast? And that's what we're really going to talk about here is the binary number system. Before we really begin to talk about binary, though, we need to go back to elementary school for just a moment and talk about the decimal number system. Decimal is the one we're most familiar with. It's a number system that's used by most cultures, and that's probably because human beings have 10 fingers, and it's just easy to count that way. But there are other number systems. You don't have to use 10 symbols. Decimal is called base 10, and the reason it's called base 10 is there's 10 symbols, 0 through 9. Now, it's not only these symbols that allow us to encode numbers this way, it's this concept of place values that we learned in elementary school. So that in the base 10 system, each place value is 10 times the one before. So we have the ones place, the tens place, the hundreds place, the thousands place. So if we have a number like 365, it's understood that what this number means is 3 times 100, 6 times 10, and 5 times 1. So in decimal, 365. We've used that for so long that that just seems like the only way to do things, but it's really not. In binary is actually base 2. And what that means is there's only 2 symbols that we use to represent everything, and that's 0 and 1. So we can represent the same numbers, it's just going to take more digits. You still have to have the concept of place values. Now in binary, because each symbol can represent 2 things instead of 10, each place value is going to be 2 times the one before it, because we can only put 2 things here. In decimal we could put 10, and so once we got up to 9 we would have to roll over into the next place. Here, once we count up to 1, we have to roll it. So you can see that we're going to need a lot more places to encode the same information, but let's look at how we do that. Okay, so every place value is 2 times the one before that. So this would be the 32s, and we can keep going, 64, and so on. Anyway, let's look at a number in base 2 and try to figure out what that number is in base 10. So here I'm going to put a number in binary, and we're going to use the place values to figure out what that number is in base 10. We might encode this as a question and say, here's a number, which I've written up there, in base 2. The subscript means it's in this base. What is that number in base 10? And so what we're actually doing here is we're going to convert a number that we have in binary into base 10. So the way we do that is just add up the symbols times the place value. Same as we did in decimal, but it's easier in binary because you've only got 2 symbols and the zeros don't count in making up the number. So 1 times 16, we just take the 16. The 16's got a 1 and the 4 and the 2 and the 1, so we add those up. 16, 4 is 20, 22, 23. So this number is 23 in base 10. Let's do another number so that we can see how this, make sure we understand how this works. But it's pretty easy to convert from binary to decimal. You just sum up the symbols times the place value. So let's do another number. Let's take a longer number, maybe. How about this number? 101010 base 2. What is that in base 10? And we can do this by Again, take the symbol times the place value. 1 times 32. 32 plus 8 plus 2. We can just ignore the zeros. 32 and 8 is 40, and 2 is 42. So that number is 42 in base 10. That's all you have to do to convert from base 2 to base 10 is just take the symbols times the place values. The only thing that I've seen people do here that could trip you up is to add 2 instead of multiplying by 2 in these place values. Each place value is 2 times the one before it, so it's not 1s plus 2s, 4s, 6s. You double it each time. So that's the only way that you could possibly get messed up. Okay, the other thing that we might need to do is convert from, here we've converted from binary into decimal. Let's also try to convert from decimal to binary, just so that we can make sure that we can do it both ways. So I'm going to erase this, and we'll put a decimal number up here and try to convert that into binary. We've already converted binary to decimal. So if we can work the other way, we can sort of convince ourselves that any number that can be represented in base 10 could be represented in binary. And if that's the case, then all the information that we're looking at in this chapter could be represented with 1s and 0s. So let's take a number in decimal. Let's start with maybe like 52 in base 10, and let's ask, what is that going to look like in base 2? So first, let's do this intuitively. Now, in the chapter this week, when I talk about binary, I do show over here a method for automatically basically doing a mechanical method for taking a number in base 10 and converting it into binary by saving remainders. And this technique works, but I guess it's more suited really to a machine than a person. What I'm going to show you over here is a more intuitive way to do that. So let's just look at what we have. 52 base 10, what is it in base 2? There's no 64s in 52, so we don't have to use that place. There's going to be a 0 there, so we can leave off leading zeros. So when we have a number, we're going to write down the place values up to, but not including the number that's bigger than the number we're going to try to do. So 52. There's a 32 in 52. And when we subtract that out, we're left with 20. So we've got to represent 20. There's a 16 in 20, which leaves us with 4. So 32 and 16 is 48. That's 52. These other ones are just zeros. So 52 is 1, 1, 0, 1, 0, 0, base 2. That's how you convert from decimal to binary. So now every number can be represented as a series of 1s and 0s. What does that really lead us to think about? Like, let's take this number here that we have, 52, and I'll get rid of this place value that we don't need. Because binary can be represented on switches, we talked about that in a previous podcast, we could represent this number here as a series of switches, with the 1s being closed switches where the switch is down, and 0s being open switches where the switch is up. So closed here, open for this 0, open for this 0. So here, 1, 1, closed switches, 0, 1, 0, 0. So open switches representing 0s and closed representing 1s. This is a model for how numbers are stored on the computer in the transistors that are in the integrated circuits now inside the computer. This is how this number would be stored in switches in the computer. So also we can look at how data would be transmitted. Data is actually transmitted, I guess, again, as a model for how that's done. We could think of data as being transmitted as a series of voltages, so that we could say that if we had no voltage on a line like this, 0 volts, that we're going to have that represent a 0. And if the voltage goes up to, let's say, 5 volts, that's going to represent a 1. So here we want to represent this number again as voltages. So we have, it goes up to 5 volts and stays there for another bit here, a bit being a 0 or 1. It goes down for this one, for the 0, back up for a 1, down for the 0, and it stays down for the second 0. So this is a model, the switches is a model for how data is stored. This is a model for how data is transmitted across the line. When you key in a letter on a keyboard, what's actually being transmitted is not the letter. There aren't any letters in the computer. There are only numbers. What's really being transmitted is a number. Let's say that you key in a D. What's being transmitted here is the number 68, and the way it's being transmitted is this series of voltages that represent the number 68 in binary. Everything in the computer is stored in binary, and what I've tried to do here in the last couple of podcasts is set up a model so that you can understand how data is actually stored at the lowest level of the computer. So I hope you've enjoyed it, and I'll talk to you again soon.